Work it, make it, do it, make sense.
Hello, everybody. I'm Daniel Lebrero. Thanks a lot for coming. And we are here today to talk about resilience, Docker, and property test. Before we get started, really quick about me. I've been working on the JVM for 17 years. Have built all kinds of applications in all kinds of architectures. I'm working right now as a technical architect for IG. IG is the world leader on CFD and spread betting. It's part of the FTSE 250, and it has development centers in London, Krakow, and Bangalore. And one of the things that we do at IG is build microservices. So I was recently involved in one of those projects, and we built this new microservice. And I need to press button. What's going on? Yeah. So we have to build the service, and it has a very simple service. Its only job was to move some messages. Oh, my God. And I broke everything. Oh, God. Give me a second. Second. Whoa. Yeah. Sorry about that. Its job was very simple. You just have to move some messages from Kafka to a third party. So we put this first version in production, and everything was working perfectly fine. But then we noticed that some messages were getting stuck there in Kafka. So we looked at the logs, and we found a bug in an open source library that we were using to consume from Kafka. So we raised an issue. The issue got fixed, and we deploy our second version into production with the second version of the library. And everything was working fine, but then some days later, half of the messages, somehow, they started to get stuck in Kafka. So we look at the logs, we did some thread dumps, we found the issue, and it was basically in the same library. So we raised a pull request, it got fixed, and we put the new version with the new version of the library into production. And everything was working perfectly fine for some days. But then some days after, messages got stuck again in Kafka. So we did our investigation, we looked at the logs, and we found the issue again in the same place. So by now, you can understand that we were not very confident that this library was the right choice. So we did what any good development team will do. We decided to build our own, because we don't write any bugs. So we put the new version of the library, the new version of the service into production, and everything was good for some days. And then somehow we managed to duplicate all the messages to that third party. So we looked at the logs, we did some thread dumps, some heap dumps, and we found a bug there. Yeah, big surprise because we never write bugs. So we put the new version into production, and everything was good for some days. And then some days after, everything was good. So we were really proud of ourselves, just one bug, that's very good. But then some weeks after, messages got again stuck in Kafka. Investigations, a little bit of cries, and you know how it goes. And we found the bug exactly in the same place. So right now we have been running with the 6th version of this service in production for some months. But I'm sure that there is still something there that is going to blow up at some point. So you may be wondering, well, don't these guys write unit tests? And of course we do. We write plenty of unit tests, but all these issues, all these bugs, happen on the integration points between components. And they all happen when the component was either misbehaving or when the component was having some stability issues. So the correct question to ask should be, don't these guys do resilience testing? Before we answer that question, let's define what is resilience testing. So if we look in the dictionary for resilience, we have those two entries. We're just going to focus on the second one. Resilience is the ability to recover from or adjust easily to misfortune or change. So what does it mean for our IT systems to be resilient? The first thing is that they need to adapt, they need to cope with any component going bad. And when we say adapt, it doesn't mean that they need to be running at full capacity or they need to provide all the functionality. Adjusting can mean that they have to gracefully degrade to cope with that bad component. The second is they need to recover. So once the component is fixed, the whole system, without manual intervention, it should go back to its initial state. So it should go back to full functionality and full capacity. So resilient testing is just checking that our IT systems, they have these two properties, yeah? To be able to adjust and to be able to recover. So back to the question, don't we do resilience testing? So at IG, we try to follow all the patterns from the released book. But we struggle with one of those patterns. That's the test harness pattern. If you haven't read the book, the test harness pattern is really simple. It only tells you to be really mean, to be really, really evil with your application. And the book, it gives you some examples about what does that mean. So you read the book, and then you go to your platform guys, and you ask them these reasonable questions. Can you please kill the database? Can you please limit the bandwidth to 1 byte per second? Can you please unplug the disk from the GMS server? Or can you please flood the network? But I always get the same answer. No. So what kind of resilient testing we can do if we cannot do all those stuff? But to understand why we get always that negative, let's look at how we do resilient testing at IG. So the first thing is that we are running our resilience test in our staging environment, which means that if we inject any faults, the whole company can potentially be affected. The second is we are running all the resilience tests manually. So we have a wiki, and in the wiki we'll have all the steps about what we want to break and what we want to break. And then there has to be some poor soul that has to go and run those things manually. We also have a role plan, again, at the end of the wiki page, with all the actions to recover. And we know that when you do things manually, what happens, right? Because of all these three, we usually limit ourselves to stop and start some of the components in the system. And we usually avoid trying to touch any of the shared components. Running any of these tests is very expensive, right? We need to get the platform guys, the QA guys, the developers, and some architects into a room, and they have to agree about what we are going to break and when, and then we have to go and manually run all these things. And because it's very expensive and it's very cumbersome, what we usually do is just run the resilient test once before we put the system in production, and then we usually don't bother anymore. So what do we really want? We want a completely isolated environment where we are sure that we are not going to affect, we are not going to bother anybody in the company. We learned a long time ago about how nice are automated tests, and the same for rollback. We want the rollback to be completely automated. But in the case of the rollback, we also want to be completely sure that the rollback plan it's simple and it's consistent, because we don't want to have any lingering faults in the system. We want to be able to inject any faults that happen that can happen in production. So not just stopping and starting some of the services. What we want to be able is to mess around with the network or break some disks. We want to be able to do anything that can happen in production. Of course, we want the tests to be really cheap to write, and we also want them to be really cheap to run. And last, we want to be able to run all these tests in our continuous integration environment, or whenever a developer feels like. So what tools can we use to get all of this? The first one is Docker Compose. Docker Compose is part of the Docker suite, and it's going to allow us to define a whole environment in just one file. And it's going to allow us to start a whole environment with just one command. As part of starting that environment, it's going to create a private network where we can mess around and inject faults. Docker Compose is also going to give us the ability to with just one command, destroy the whole environment. So that this gives us our rollback strategy. That is just going to be burn everything to the ground and start from scratch. The second tool that we need is some kind of library to be able to play around with the environment and to be able to simulate those faults. So IG has open sourced a library called IG Havoc that is going to give us three things. First, it's going to give us an API to be able to start and stop or restart or kill some of the components. Second thing is going to give us an API to be able to inject faults in the network, like, for example, delays or limit the bandwidth. And the third thing that it gives us is an evil HTTP server that we can use as a base to create to mock our third-party dependencies, our external dependencies, and it's also going to allow us to simulate faults in that external dependency. So, for example, returning always a 500, or return a huge or an infinite response. Now, you can use these two tools for, it doesn't matter which language or runtime do you use. As long as it runs in Docker, you can use these tools and this approach. And the second thing is that you don't need to be using Docker in production to use them. As long as you can run it in your laptop or in your CI environment, it's a useful thing. So let's look at an example about how to write a test. So this is the architecture for the system that I was talking at the beginning. Just as a reminder, the system, the only thing that we need to do is move messages from Kafka to a third party. That third party is an HTTP endpoint. Now, because we are going to run a test, we don't want to talk with the real third party. So what we are going to do is we are going to replace that third party with a fake server. And this fake server, we are going to use it for two things. First, we are going to use it to record all the messages that we get from that service that we are building. And the second thing is, as I said, just to simulate, just to be able to inject faults and pretend that the third party is misbehaving. Each of these boxes will be one Docker container. Okay, so let's look at a Docker Compose file to be able to build that system. So this is all that you need. So one bit at a time. That's just how you create a Zookeeper. So this is just one of the Zookeepers. We will have 3 of these entries. And we're just using a vanilla Zookeeper from Docker Hub. So it's very simple to spin up a new Zookeeper cluster. The same for Kafka, just a vanilla Zookeeper, a vanilla Docker image. And notice that we are going to run it in privilege mode, because to be able to inject faults into the network, we actually need some root privileges. As I said, as part of Docker Compose, as part of creating that private network, it's also going to create a DNS server, so you can reference other containers by name. This is the service that we are testing. So in this case, it's a Tomcat application. So again, in this case, we are adding a couple of things into the image from Docker Hub. So we are adding IP routes and IP tables that are the 2 tools that we are going to use to inject faults into the system. And notice that the path there of what we are deploying to that Tomcat, it's a relative path, and that's because we are going to be building that WAR as part of our build plan. So we want to run this test in our continuous integration environment. And last, fake server, which is just a Java application, so very simple. And notice that we are going to be exposing a port. So for our test to be able to connect to that fake port, to that fake server, and to be able to know what's going on inside the system. Okay? So let's write our first test. For our first test, what we are going to do is, our system should be able to work if one of the 2 instances is down. So we're going to have Maven, and we're going to use something like JUnit to be able to run it. So the test, what it's going to do is first it's going to start the whole system, user token compose. Then it's going to kill one of the services. Then it's going to connect to Kafka, and it's going to send a bunch of messages. Come on. And then it's going to connect to that fake server through that port that I was talking about to check if we got all the messages. And then we are going to tell Docker using Docker Compose to get rid of the whole thing. Okay, so that's our role plan, which is going back to a clean state. So let's look at a little bit of code. For those not familiar, this is Clojure. Let's go one line at a time. When you start Docker, when you tell Docker Compose to start a whole environment, you have to give it some kind of ID. So if you're running this in a continuous integration environment, you need to make sure that that project name, is called project name in Docker Compose, it's unique. Yeah? So if you have several branches, or if you have several plans, you have to make sure that that project name is unique. This is how you define that. This is like a unit test in Java, a JUnit test. So that's basically the same thing. And then this is the first step to start the system. So we're just using the Docker Compose command line, using the Java shell to start it. And as I said, we're using there the project name. Then we create a Docker object, and we are specifying there that's the Docker API. So we are going to use that from the test to be able to connect to Docker and run the commands. And then we tell Docker to run a command, which in this case is to stop service number 1. Other examples, this will be, for example, to restart. And if we wanted to inject between 5 and 50 seconds latency between service 2 and the fake, that's how a command will look like. Then we send a bunch of messages, and here's where we are doing our assertion. Yeah? So we are saying that we expect that within 5 minutes, we receive the 20 messages. And we are giving it a little bit of time because we are sending things asynchronously, plus the system, if we are injecting any faults, maybe needs some time to detect that fault and recover and adapt to that fault. And last, we just stop the system, again using the Docker Compose command line. Yep. So we have written that test. Probably now we want to write more tests, right? Probably we want to make sure that our system is able to cope with one of the Kafkas going down. Or maybe we want to check that what happens if one of the services is not able to talk with the Zookeeper cluster, or if the service has some problem talking with the fake. Or maybe what happens when those two things are broken, or those two things, or maybe those two things, or maybe those three things. If you are good at math, maybe you are now thinking about, well, there are 14 things that can break. Maybe they can break in 4 or 5 different ways. So how many tests do I need to write to cover all those cases? So the answer is that there is an infinite number of tests, because in the case of resilient testing, it's not important just if the state of a component is up or down. It's also important the order on which things happen. Yeah? Now, if you are like me, you're probably thinking, oh, come on, let's be serious. You know, most of those faults, they are not going to happen in my environment. That's completely impossible. But I have a more famous quote. That's, I didn't expect that. Because if I have expected that, I probably will have a piece of code to handle that particular case. But in the case of outages, what usually happens is that something impossible, it becomes possible. So where we are, we know that we want to write some tests, but we are not sure which test we want to write. So how do we go about it? So one option is property-based testing. Who is familiar with property-based testing? Cool. I'm going to explain it. Sorry about this. I'm going to explain it very, hopefully, quickly. Let's say that you have write your own plus function, and you now want to test it. So in the case of example-based testing, which is the testing that we do every day, your unit testing, what you're used to, what we are going to do, or what you will do, is pick up 2 inputs, like, for example, A equals 6, B equals 2, and then you will assert that A plus B is 8. So you are picking up those particular values. And then maybe you will say, OK, I'm going to test with negative numbers, or I'm going to test with 1 positive or 1 negative. So you are specifying each of the inputs. In the case of property-based testing, what you do is you specify all the possible inputs to your function. So in the case of A, what we are saying is that Well, it can be any number, and B can be any number. Now we have the problem of what can we assert, because in your code you're not going to know if A is 6 or 9 or 25. It can be any number. So we have to assert something that is true for any number. So that's called a property. So in this case, a possible property will be that A plus B is equals to B plus A. Yeah. Once you have written this test, what you will do is tell the library, the property-based library, to go and run 100 of these tests or 1,000 of these tests. And what the library will do is first it will generate a random A, then it will generate a random B, and then it will run your assertion. If the test passes, so if your asserts are true, if your properties hold true, it will generate another A and another B, and it will run the assertion again. And it will do that as many times as you tell him. Now, if the property, if it's false, so if that assertion fails, what the property-based test library is going to do is trying to shrink the value. And by shrinking the value, it means that it's going to try to find the smallest value on which that property, that assertion, still fails. So let's look at a very simple example. Let's say that you write that's your plus function, and you have that little bug. So if A is bigger than 100, it's going to fail. So if we run the property test, we are going to get an output something similar to this. So let's focus in those two lines. What those two lines are telling us is that the library was able to generate 106 cases, 106 random A's and random B's, and everything was fine. But then on 160th time, it found that the property fell. And it fell with those two particular values. Yeah? So if you have A equals minus 39 and B equals 104, then the property fails. But then it does the shrinking. So in the shrinking, we try to find, in the case of numbers, we try to find smaller numbers, numbers close to 0. And it's able to tell us that if you try the same function with 0 and 101, and notice it's 101, then your properties fail. Yeah? Apart from that, it's going to give us a seed. So if we want to run exactly the same test with exactly the same inputs, you can use that seed to generate the same inputs. And that's basically it, property-based testing. So first thing that we need to do, we need to decide what are the properties. So in our case, for resilient testing, for the system that we are talking about, which properties do we have? The first one is that we want to make sure that each message, it gets at least once to that third party, right? The second one is because it's at least once, it means that we allow some duplicates, but we don't want a lot of duplicates. And the third property is that Kafka is a topic, it's something that's in order, so we want to make sure that when we send data, there is no way that old data overwrites new data. Okay, so those are three properties that doesn't matter what happens, they should be true for our system. Now, what kind of input do we have for our resilient testing? So in the case of resilient testing, the input, it's all the possible faults that can happen in any order into the system and all the possible recovery actions for the system. Yeah, so we need to basically generate a random resilient test plan for our system. So IG Havoc comes with a function to be able to generate those random resilience plans. So that's the function. And what we are specifying is which things we want to break. Yep. So in this case, we are saying that we want to break the service 1, service 2, Kafkas, and we want to break the link, the network link between those two components. Then we specify how many entries we want in that plan, and what this function will return is a resilient test plan like this. Yeah? So in this example, stop one of the Kafkas, breaking the network between service 1 and the fake, and then stop off one of the other services. Now, you think about it, if we generate just random commands in our system, we can end up in a situation like this. In this situation, it's impossible that those three properties are going to hold true, because nobody's going to be sending anything to the fake server. So it's not enough to just generate random commands. We also need to specify what are the healthy states of our application, so in which states we expect the application to be working. So in the library, so a part of deciding what things you want to break, to play around with, you need to specify which are the healthy states of the application. So in this case, we are saying that there are three states. Both services have to be up and running, or service 1 can be stopped, or service 2 can be stopped. Yeah? So one of the two services have to be up and running. So now if we generate a random plan, a random resilience test plan, we can get something like this. We stop first service number 1, we stop service number 2, and now is when the system is completely broken, but the library will make sure that the last set of commands take you back to one of those healthy states, which in this case is just to start service number 1. Cool, a little bit of code. That first thing is just how you call the library, and in this case we are saying, oh, run this test 100 times. This is the input to our, this is the input to our, this is the input to the library. So we are saying, okay, generate random plans, and notice that we pass all things that can break and all the healthy states. Then we start the system as we were doing before. We create the Docker, and we start an asynchronous thread sending messages. Yeah. And while that thread is sending messages, so while there are some messages floating around the system, what we do is we are going to execute our resilience plan. So we are going to do, for each of the steps on that plan, we run it, and then we wait 10 seconds. And we are giving it, again, a little bit of time to the system to be able to recover or to detect any faults. Once we have finished the plan, we are going to wait for those 20,000 messages to be sent, and then we check our properties. This is where we are checking them. And the three properties that we are checking, it's first, we expect exactly 20,000 messages or unique messages because they have an ID. We want to make sure that each of them was received by the fake server. Then we check the duplicates, which in this case we are saying that around 10% duplicates, it's a reasonable amount. And then we check that old things doesn't override new things. And then we stop the system. So, does this work? If you think about it, we are generating a random set of a random resilience test plan, but the number of tests that we have is infinite. So, is this able to work? So, in our experience, we were able to reproduce the first 4 outages with that test that I just showed you. Yeah? And some of the issues were not really trivial. So, for example, for the outage number 2, to reproduce it, you need to kill that Kafka, restart that service, you start the Kafka again, then you restart that Kafka, and at that point, that service is not able to consume messages from that Kafka. So it's not something that I will think about it. Now, if you remember, we talk about 5 outages. So what about version number 5? So we ran this test for hours, days, and we were unable to reproduce the issue. But then somebody realized, well, okay, wait a second, what are we doing? We are starting the system, then we send a random set of commands at the same time that we are sending messages. We do our assertion, we stop the system, and then we start it again. So somebody says, well, how do we fix everything in IT? So we thought, well, maybe on that restart is when we are actually cleaning some bad state. So we wrote another test, which was, we start the system, we send the 20,000 messages, plus we run the random commands. Now we make sure that on those random commands, we never stop or restart any of our services, so we'll make sure that our service is up and running. Then we do the assertion, and then we start back again. With this test, we were able to reproduce issue number 5 after several hours of running. Now, in the case of issue number 5, the issue was that if the third party returned a 401, and it had to be a 401, if it was 400 or 500, it was okay, but if it returned a 401, and then we send 200,000 messages, then the system will stop working. So the problem with this approach is that what I talk about shrinking doesn't work anymore, because you don't know if the cause of the failure happened in the last iteration of messages, of commands, or it actually happened like 10 or 100 iterations before. So shrinking in this case is useless. So what about version number 6 that had been running happily in production for several months? We found out one off-by-one bug. I think we all have one of those, even if you don't know it. It was interesting to find that we found 2 race conditions in the test code itself. We found that if the third party returns 401s, we lose messages, so at least it doesn't crash, but we lose messages. We will start sending duplicates like crazy if we don't get a well-formed JSON response. Any huge response from that third party will kill our service. We also found a dependency on the startup of our components, and we usually try to avoid any kind of startup dependency. We also found, the test remind us that our Kafka setup it wasn't resilient enough. This was interesting because as part of generating the random plan, we need to specify what are all the healthy states of your application. One of the tests that we wrote is, okay, we have all the healthy states, so we wrote a for loop, basically, saying, okay, I'm going to test each of the healthy states to make sure that it's actually true. And what we found is that a lot of the healthy states, what we expected to be a healthy state, was actually not that healthy. And the last thing is that between version 5 and version 6, we actually re-architected the system. And it was interesting to see that version 6 have a bigger proportion of healthy states, which means that version 6 was, by definition, it should be more stable than version number 5. Cool. What are the drawbacks of this approach? The first thing is that it's very, 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 very slow to run. So a test like that can take several hours. We sometimes leave it several days just running to see if we was able to find something. Sometimes, like as I explained for the bug number 5, shrinking is useless. Then we still have non-deterministic in the system, right? We are doing things in parallel. There are a lot of threads going around, so it's possible that you hit an issue and you are not able to reproduce it again. You will still have an infinite number of tests, which means that it doesn't matter if you have been running this thing in production for, if you have been running the test for hours or days, you are not sure if you have any bug. In fact, version number 6, we had another outage. This time around, it was an out-of-memory error. And it doesn't matter if we run the test for days, because the issue was that the test was sending data to one Kafka topic. But in production, this application was actually consuming from 10 Kafka topics. And in our test, we made the assumption that sending it to one topic should be the same as sending it to 10 topics. So we're a little bit lazy. And production showed us that we shouldn't be lazy because we have another outage. But there is this nice paper called Simple Testing Can Prevent Most Critical Failures, where they do an analysis of 200 outages in distributed systems like HBase or Cassandra. And of those 200 outages, they found that 74% of them were deterministic. Yeah? So if you execute the same 3 commands in the same order, you will always be able to reproduce it. And also they found that in 90% of the cases, you just need 3 commands, 3 things to happen to manifest the system, to manifest the failure. So maybe that's why we were lucky and we were able to reproduce all the issues. So, takeaways. Docker is your friend, and don't write tests. Thank you very much. Sorry. When I say don't write tests, just to make it clear, I'm saying state your properties, check your assumptions, and let the computer do the bearing work. Thank you very much. Some references. If the last two papers are a different approach, they're really interesting. So just have a read. They're really, really interesting. And with that, I'm done. If you guys have any questions, happy to answer.
So I think it's great. We're trying to get there. Sorry. Yeah. Okay. So I think it's great, and we're trying to get close to this. We see some of the unusual paths of system failure that you're seeing when one of the dependent systems, such as solar, is attempting to rebuild indexes and isn't ready to be taken over by the other system failing. But everything that you have here is still on stage, as opposed to in production.
Yep.
And a number of the systems that we are dependent upon, despite our best efforts, don't belong to us, and their stage versions are not the same as the production. So do you have anything that helps you do a similar kind of thing, but in production?
Cool. So the first thing is Chaos Monkey. Cool. So our problem is not a problem with Chaos Monkey, it's a problem with ourselves. Chaos Monkey works great if you are running in Amazon cloud. We are running on premise, which means that we are not able to get close to production because the fix from Netflix guy is just like, I destroy this cluster if it doesn't work, and I create it in another place. We cannot do that. So that's why we cannot use that. Now, doing these things in production, we still we are not. I don't think ever going to do that. So I'm really not sure how to. A part of mocking the thing, because you don't. In theory, you are doing your testing, so you don't want to hit that third party. So just try to mock it. Is that impossible? Is that completely off fake it? Is that completely out of?
We've tried. So I'm with you. I think we're in the same place, which is what I'm trying to determine. Thank you.
More questions? Just a second.
That fake server for the third party. How did you make sure to have all the kinds of failure states of their original system in the fake server?
Okay, so it's an HTTP endpoint. All HTTP endpoints fail the same way. You either get a 500, or you get no response, or you get a malformed response. So it's HTTP. So it really doesn't. So in this case, we are not looking at if they return a particular, or in this particular case, it's not important if they return an a well-formed JSON that contains an error inside it. So from our point of view, it's just an HTTP endpoint. Yeah? So we'll just test it as any generic HTTP endpoint, the same failures that you will expect. Yeah.
Like you kind of answered my question already, but how often do you run these tests? And well, my initial question was, how long do they take? So.
So right now it's ad hoc. So we haven't put it in a continuous integration server. The first thing is because we don't have Docker in our continuous integration environment. So first I need to convince the platform guys to give me Docker. So we're doing it ad hoc right now in the developer boxes. It's like, just run it. I'm going to leave it overnight to see if I find something next day.
Can you apply this tool only to Docker, or can those commands be any arbitrary commands?
Sorry,
can you apply this tool only to Docker containers, or can it be actually any
I think it's just Docker. Well, it has everything. In theory, it's the same as, there is similar things like Jespen. I don't know if you guys are familiar with Jespen. There are a bunch of tools that do this failure injection, but they are usually depends on the platform that you are running it. I copy most of the failure modes from Netflix Chaos Monkey. It's just I needed to go through the Docker API to be able to apply them instead of what they are doing with Amazon. So you can copy the failures, how to do the failures. It's just a matter of how you are going to deploy that into, or how you are going to apply that into your environment. Anything else? Cool. Thank you very much, guys.